Hi everyone, and the next session will be the talk from Rowan McAllister, and Dr. Rowan McAllister is the Learning from Interaction team at Toyota Research Institute, and he completed his PhD from the University of Cambridge in 2017 and a postdoc at the University of California, Berkeley in 2020. And he's working on probabilistic modeling towards data-efficient reinforcement learning and autonomous vehicle planning. And for today's talk, Rowan will talk about robust behavior models for autonomous driving. Okay, without further ado, the stage is yours, Rowan.
Thanks, Xunshe, and thanks everyone. Just to start off, can you see my slides? You can see it, great. Thanks so much. Well, yeah, thank you so much for inviting me to this workshop. Yeah, what a great set of speakers and organizers and topic. So I'm gonna jump right in. So basically, I was wanting to talk a bit about robust behavior models for autonomous driving, and basically the kind of theme of this talk is really about this. Is in many driving situations, often the major source of autonomous driving uncertainty is the other agents on the road. You know, we might be able to perceive them, you know, mostly fine. There's always exceptions where perceptual uncertainty matters a whole lot, but in many kind of, say, highway driving scenarios, we can often see other agents just fine, but we often have a very good idea of our own dynamics as well. There's usually no process noise concerned with our own vehicle in many normal driving situations. And so really, you know, for many situations, it comes down to the fact that we don't know what other agents are going to do. Occasionally they'll use their blinker and stuff like that, but we really have kind of very little idea about their goals. And so in terms of the future of the road scene, this can be you know, a big issue that really needs to be modeled correctly if we want to be able to drive safely. So in principle, you know, probabilistic behavior models or trajectory forecasting models can help in these kinds of situations, you know, if they are accurate. And so yeah, the big kind of condition here is, like, you know, are they accurate? Because, you know, if we're using any kind of, you know, probabilistic MPC or anything like that, it's really relying on our behavior models being accurate. Any risk-aware planning is the same. It's only as good as how good our models are. And so in this talk, I wanted to talk about two ways that we could, you know, robustify these behavior models based on how we're actually going to be using them downstream. So part one of the talk will be talking about a project that we recently published that is to do with planner-aware prediction. And the second is something we're about to throw in archive, which is a project on risk-aware prediction. So let me jump straight in to the first one. So the first one, its full title is Control-Aware Prediction Objectives for Autonomous Driving. And this is work with several collaborators at Toyota Research Institute and also Berkeley. And so I wanted to start off with, like, you know, asking you to consider, if you were an autonomous vehicle witnessing a scene like this, and say you're driving down this lane, what would you be thinking? You'd probably be thinking, well, there's a few pedestrians on the road, and we probably want to forecast some of their motions. So consider this pedestrian here. Say we make a prediction that this pedestrian walks this way, when in fact they walk this way. One question is, does this prediction error matter? Now, consider the second pedestrian over here. Say we predict that this pedestrian walks to a stop, when in fact they run to make the green light. Does this prediction error matter more? So in our work, we want to talk about how this second prediction error, even if it had the same L2 error as the first prediction error, actually matters a whole lot more, because it looks like it may cross into our path, and we may actually keep going if we assumed that that pedestrian would stop, and this could actually result in a collision. So this has the greater real-world consequence. Okay, and so a problem in the literature is that forecasting metrics are typically unaware of their usage. For example, as an input to a downstream planner. And this is a problem called objective mismatch. So our proposed solution is to weigh forecasting metrics by their effect on downstream control. And the benefit here is that this improves forecasting accuracy where it matters most. So for instance, potential collisions, a pedestrian, from a pedestrian potentially stepping out onto the road. And there's many forecasting metrics used in the literature. Some of the common ones used in various papers, and also motion prediction competitions from like Waymo and Argoverse and Lyft and so forth. Things like average displacement error, or final displacement error, or the minimum versions over these, taking multiple samples, which is helpful for multimodal prediction or scoring multimodal prediction. Also things like the miss rate, or for probabilistic models, often the log likelihood or negative log likelihood as a loss function. But there is also several works that but one of the flaws of the prior metrics is that none of them will consider how they are used downstream. There are some other works that do actually look at how how a prediction model will be used downstream, and different works will make different assumptions. And so some of the are things like, is the planner differentiable? So this is common in end-to-end methods, also any methods that are looking at, for some kind of local sensitivity analysis. If their prediction changes by a little bit, would a downstream planner be sensitive to that, and should they weigh that higher, for example? Or a second one is a planner stochastic. So this is kind of useful for methods that are using some downstream policy gradient method, a type of reinforcement learning. And also, is the, can we make the assumption that the planner is a known function? Often it's not, but it's often useful for, often it's not for the sake of computing a prediction model. But if it is known, it's useful for computing counterfactual actions, like what would the planner have done if we made different predictions? And so in this work, we really consider the last only, since many real-world autonomous vehicle planners are actually human designed for reasons of safety and verification. So we do not really assume anything else, including the first two. So our method that is upcoming, I'll describe in more detail on the next slide, is able to handle usage with planners that are differentiable or not differentiable, stochastic or not stochastic. Okay, and so our method is actually very simple. It's really to weigh forecasting metrics by their effect on downstream control. So we compare against a baseline, in this case, the reparameterized push forward policy, or R2P2 for short, which uses the likelihood metric for scoring trajectories. So our work here is simply to reweigh this metric. It could be any metric, but in this case, we're using the likelihood in several ways. So here, what we're doing is we're weighing the expected difference in controls compared to if the controller had been fed the ground truth trajectory, in this case, Y, where the controller or planner is given by pi. compared to the predicted trajectory, in this case, y hat. So this is our estimate of, say, where a pedestrian or a vehicle in front of us may move in the future. Or in this case, a worst case version of the above. So if we sample multiple times, say we've got a probabilistic model, we could take the worst case discrepancy between controls that we would take if we knew the future compared to the controls that we take if we are using a prediction from our behavior model. Or finally, a different kind of attention weighting that I'll talk about next as well. So these are just different ways of reweighing a pre-existing objective that we've used to train a predictive model. And we can see how they go later. And just to give a bit more detail to the attention method, the attention weighting really uses the attention matrix from multi-agent trajectory forecasting, which reflects how much the ego vehicle's trajectory is a function of other vehicle or pedestrian trajectories themselves, as if we were predicting the ego's trajectory without knowledge of where it's going. Okay, so those are the three methods. We use the Kala experimental platform with a single ego vehicle, and in this case, multiple pedestrians that are sometimes crossing the road. So our controller will slow down if a pedestrian is predicted to cross the path of the ego vehicle. So for example, this pedestrian circled in green, but not the pedestrian circled in blue, for example. And so here's a visualization of the attention weights that I was talking about as our third method. So we can see which pedestrians matter more. Generally, the pedestrians that we want to weigh higher on the right, they're closer to us because we're driving on the right in this case. And in this case, we've got a top-down view. Notice the attention, which is signified by the width of these lines between our ego vehicle and the pedestrians. It's definitely higher for pedestrians that are in front of us. Obviously, any pedestrians that are well behind us, that's not really going to affect what we're going to do. So in effect, they don't matter with respect to what the ego vehicle needs to do or how it will plan. Okay, and so our experiments, there's some different experiments in the paper, but just to summarize very briefly here, our experiments show that by weighing forecasting errors by their effect on the downstream controller or planner, we can improve the metrics that we really care about, namely things like success rate or the reciprocal here, which is the number of collisions in that particular environment. And notice this comes at the, interestingly, this comes at the expense of traditional forecasting metrics like the average displacement error. So here, our three methods are actually doing worse than the baseline, but our argument is that this doesn't really matter. The thing that really mattered was the collisions. And so interestingly, the middle method that considered the worst case scenarios by taking multiple samples and computing the largest control discrepancy as a form of weighting is something that ended up being the safest. So we were able to reduce the collisions down about tenfold. Okay, great. So that's the first paper I wanted to talk about, which was planning aware prediction or control aware prediction metrics. The second one is to introduce a notion of risk awareness. So this is primarily work by Haruki Nishimura and Jean Macat at the Toyota Research Institute. So here we've got a similar scenario where we've got a potentially dangerous situation coming up, and we want to be able to focus on things that are not so much likely, but things that are important. So for example, given the bicyclist's past path here, we may be pretty sure that they're going to drive parallel to us, which might be safe. But there's always maybe a small probability that they could actually cross our path. And this is actually something that we want our planner to always be aware of, even if it's a low probability event, especially if it's an important event. So here, basically, the theme is that, just because something is uncommon does not necessarily mean that it's unimportant. So often, the tail, especially, and this is especially true at the tails of different types of driving scenarios. Often, things that are, uncommon can be, often out at the tails of like different types of scenarios that we might see. They might actually be disproportionately responsible for safety infractions. Okay, so typically a risk-aware planning architecture might look something like this. So we've got the state of the system. We're doing some kind of probabilistic prediction. In that case, the cyclist could have turned left across our path, or they could have kept on going with the flow. It was multimodal. And then often with risk-aware planning, there's some kind of risk-aware function, a function of the distribution of costs that we would associate with the different modes. And then this can be used to optimize a policy that gives result to a next action that we might take. So this is a typical way of doing risk-aware planning that is sensitive to the distribution of possible costs associated with a cyclist's path. And so here, this is what we've seen before. Maybe there's a chance that they cross us, but probably not. And so if we were to look at the distribution of costs, we can see here that, I hope you can see my cursor, but we can see here that most of the costs are very low. But there is a chance that we do get some costs that are very high up here if we were to score these different trajectories. And so typically what a risk measure will do will be a function or a functional of this entire PDF distribution here, and have something that's a little bit conservative. So often something that's between the expected cost and the maximum cost. And an example is the CVAR, which I'll talk about in a second. And so our work here is to actually really flip the script a bit and to say, can we come up with risk-aware prediction instead of planning? So this really puts the onus on any type of risk assessment that we want to consider here. Can we consider this during prediction? So instead of using a model P of the true distribution about how a pedestrian or cyclist may move throughout the scene in front of us, can we use a different distribution Q? And what we're really trying to do here is work out, can we come up with some different distribution, some pessimistic distribution about how that cyclist may move, such that if we just take the expected cost under this biased distribution, can that equal this, whatever this risk value is over here, this pessimistic assessment of what is the cost going to be? Okay, and so I want to just stop here a little bit and just say, like, why would we do this? So we want this kind of, we would really like to be able to train this pessimistic distribution Q that is risk biased using a prediction loss that matches these two. And so what this does is this shifts the computational burden from drawing many, many samples that capture rare events. you could consider that, that cyclist, maybe there was a 5% chance, but what if there was only a 1% chance or a 0.1% chance that they cross in front of us? If we take from our model 20 or 50 samples, we may actually miss that. And samples can be expensive to draw online where there's real-time constraints for our planner. So what we want to do here is we want to shift the computational burden of drawing many prediction samples that capture rare events from online deployment to the offline prediction training. So the training of this Q distribution. So something where we can draw as many samples as we want, and we can take days to train. Can we train this such that we can take a quick expectation at planning time, and we get a very accurate measure for the risk? And so furthermore, this approach also eliminates the need to modify a planner's optimization algorithm if we're dealing with some big autonomous vehicle stack and we don't want to have to change the planner too much, but only the predictor. And just to talk a little bit about different types of risk measures. So we can often write down, as a function of the cost distribution, or writing cost as a random variable here. We often want some score that's between the expected cost and the maximum cost. And so two examples that are often used in the literature are things like the entropic risk, where we've got some hyperparameter sigma here that is really a temperature on the soft maximum. So this is like a log sum x per term. So you could think of this as like a soft maximum with a temperature parameter sigma. Another one that's common in the literature is also the conditional value at risk. And this equation is maybe a little bit hard to pass on first glance, but basically it means this. It's related to the expected improvement from the Bayesian optimization literature. But basically, if there is some value sigma that is talking about the percentile of cost that we're interested in, say the 95 percentile cost, we can take this point here, and the CVAR is the expected probability mass of cost past that point. So so basically we would have, say, this value here for the 95th percentile, where this probability sums to 5%. So this is a way of taking the effectively a pessimistic assessment of the cost. And so what we did in a road crossing scene was to basically train up a pre-existing trajectory model, which in our case was the CVAE. And then what we do is we train a risk-aware encoder to basically take into account a particular risk level that we want. In the previous slide, this was sigma. So how far along the tail do we want to be? And then basically bias the latent space such that when we decode, we get predicted trajectories that are more risky. So in the case here, we have a ego vehicle that is driving along. We have a pedestrian that is walking out. Maybe they will be slow and we could hit them, which is the red mode here of probability of mass, or maybe they will be fast and they crossed in front of us, in which case is the green probability mass here. And I think I'm probably running out of time, so I'll just speed up a little bit here. And this is basically what it looks like. So we might have some ground truth, the bimodal distribution of where that pedestrian will walk. And hopefully they walk quickly, which is the green mass, such that by the time we get here, they've already finished crossing the road. And so if we train our model, this is what it looked like, where we then make a risk neutral prediction. And so we can see we've still got these two modes. It's almost collapsed these two modes together, but it hasn't quite. So we've got a bit of error in here, but the risk bias prediction model is really basically biasing towards that red side, so that the more dangerous side. So this means even with just a few samples, we're probably going to get some of that risky behavior, even if that mode was uncommon. And basically to basically show you what this looks like for a scenario like that, if we're using if we're trying to compute what is the risk estimation error, if we were to just use an unbiased model, which is in blue here, we basically need more and more samples to get close to 0 here. Whereas with the biased model, we can get it almost instantly. And this is more and more true the more to the tails that you go. So the more we get to the 95th percentile or the 99th percentile, the more samples we will need from an unbiased model, which may violate our real-time constraints. Sorry, yeah, last 30 seconds. So everyone can go home. We also applied this to the Waymo Open Motion Dataset. And so we can see here for different risk levels, this is kind of early on in training, so like we haven't got all paths sticking to the road just yet. But basically for a risk level 0, this is what the predictive model looked like, and our ego vehicle is in blue, moving this way, and we're interested in what green is going to do. With a higher risk level, it's starting to bias towards predictions that will cross our path, and at the 95th percentile, it's starting to predict most of the samples colliding with our path. So hopefully if we just take a few samples here, our planner is very cognizant that this is a possibility and it can start to slow down. It's not going to accidentally miss a prediction where green may collide with us. Yep, thank you to my fantastic collaborators, Blake, Logan, John, Haruki, Sergey, and Adrian. And if you have any questions, please ask. Thanks for attending.